right, test. Yeah, I can hear myself. Hello, everyone. Let's talk some actors. First, a round of introductions. My name is Nikita. I have worked on a bunch of databases like MongoDB and ClickHouse. Currently, I work on Prisma. My main focuses are system programming and everything related to data. Before we dive into the actor land, let's discuss what they are. I'm sure lots of you have already heard about the actor model and maybe know something about it, but just to quickly recap. Actors is a way of thinking about concurrency. It's a model for concurrent programming, which in layman terms can be presented as a bunch of single-threaded tasks executing concurrently. One of the features which usually stands out in actors is the fact that there are no locks, no atomics or conditional variables involved, because there is no shared state. Your actors cannot access to the same memory location ever. Instead, actors use message passing as the main synchronization primitive, so the only way to actually talk to our actor is by sending a message. When I first encountered this model, it felt weird, to be honest. I was taught in the university to think in terms of locks and atomics, and now you're saying that, hey, I will be memcpying data all the time, but it actually has some interesting properties. The fact that each task is single-threaded makes it easily parallelizable. Consider an example of an HTTP server. If each actor is handling a single, if an actor handles an HTTP request and maybe your system is under load, you can just spawn more actors, and each of them will have, you will have the increased capacity of your system just by spawning more tasks without any code change involved. Since there is no shared state, there is no data races. I save it in quotes because there are many creative ways to create a data race with any synchronization primitives, but it is significantly harder with message passing because of some ownership. Because when you are passing a message, you are relinquishing the ownership and passing it to another thread, which makes it really hard for you to, after passing the message, modify somewhere there. Not impossible, just really hard. The fact that everything is done from message passing makes all the inter-thread communication explicit. If you have a shared state somewhere, for example, a struct, and it's hidden behind a mutex, and there is like an integer field in this struct, if your thread locks the mutex and modifies an integer field, it's not really clear what is the intention behind it. How does it affect the other parts of the system? When you're using message passing, usually the message communicates an intent. Something happened, and you would like to inform our threads that, hey, I don't know, an HTTP request has arrived, or some other event happened in my system, and you can basically search for usages of that struct to see how different parts of the system react to it. Moving on with the actor model. I'd like to present an example of a technology which uses it everywhere. So Elfo is a Rust framework that enables the developers to do actor programming. It already has all the necessary building blocks for you to construct a concurrent system using the actor model. It has the message passing, obviously, because there is no actors without messages. It also implements routing. You can decide dynamically where your message goes. It automatically handles actor restarts. If your actor panicked for some reason, it doesn't bring the entire system down. Much similar to Erlang, Elfo is able to restart your actor, and you can define policies on how that happens. Elfo supports the distributed mesh, which we'll be talking about in this talk, and much more. Before we dive into the distributed part of Elfo, let's take a look at the simple example of an actor. So, as I said before, actors are basically concurrent tasks, and that maps nicely to the async tasks in Rust. Here we have a very simple actor, which first of all sends a message with the text "Hello World," and then receives the message and checks if it is a reply to his early message. So you can send messages, you can receive messages, and both of these operations are asynchronous. While it is probably obvious why the receive operation is asynchronous, because there might be no messages, so we need to wait for them. The send operation is also asynchronous, and it might sound weird, but we will get into that a bit later in the talk. L4 also builds a couple of powerful abstractions on top of messages, such as requests. So the whole code in the previous slide can be replaced with just a single context.request, where you send the message to some actor and you get a response also in the form of message in yeah, that's a finished sentence. Actors in L4 are organized in groups. You can think of groups as general areas of business logic in your application. For example, you can have a WebSocket actor group where each actor handles some request from a browser, maybe a mobile app or somewhere else. You can also have an aggregator actor group. If you're developing, for example, an advertisement system and you want to aggregate events from actors which handle WebSockets, you might have a separate actor which aggregates clicks and a separate actor which aggregates views. So fundamentally, they are doing the same thing, right? They are computing some number statistic, but they are doing it a little bit differently because one is aggregating one kind of events and another one is aggregating views. Defining messages in L4 is as easy as defining a struct in Rust. You just declare a struct as you would normally do. You can declare any struct which is serializable. There are some cases where you can declare a non-serializable struct. We'll cover it a bit later. But in the simplest case, your struct is serializable. You just define it and add a procedural macro on top, saying that this is a message. If you define a request, the process is completely the same, except that you need to define what message are you waiting in response. So in this example, we have a greeting request, which expects a reply, in reply to the request. Before we continue on this discovery of the distributed mesh, let's take a look at how message passing is performed on single node. So imagine an example where an actor wants to send a message. Which steps does it go through? First of all, the message goes through the so-called group router. As I said before, you can define dynamic rules on where your messages end up. And if you're a WebSocket group, for example, and you want to send a message to your aggregator group, well, the router needs to know that, hey, this kind of message goes to the aggregator group and not somewhere else. Once we have established which group the message belongs to, it's then up to the actor router to decide which actor it goes to. So we are inside a group, for example, an aggregator group, and we decide which actor this message belongs to. It's important to note that all this logic is user-defined. So it is you, as a user of the framework, define which messages go to which groups and which messages go to which actors inside these groups. Finally, once the message passes through the actor router, it goes into the actual mailbox. This might seem familiar to many of you. This is just a Rust channel which contains all the messages. So if you worked with crates like Futures or maybe Crossbeam, channels might be familiar for you. An interesting property of messages in L4 is that sending a message can actually fail. It might not make any sense in the beginning. Like, we're sending a message on a single node. What's there to fail? Memory, like if we are handling memory failures, we are in a big mess. But when you try to send a message, for example, the group router might decide that, hey, this message does not belong anywhere. I do not know which group needs to handle it. In the same way, the actor router might not be able to find an actor this message belongs to. For example, your actor for some reason panicked and was not restarted yet, so there is literally nowhere to send the message to. Finally, the actor's mailbox can be full. We intentionally limit the size of a mailbox because different actors can work at different paces. For example, one actor can produce 100 messages per second, but another actor can handle only 50. This means that if we just allow the first actor to send messages infinitely, we'll just allocate more and more memory to buffer all these messages, and finally we will run out of memory. So we need some kind of a back pressure mechanism from the actor mailbox saying that, hey, that's enough, I have 10,000 messages, I can't handle any more, wait until I will handle my current work. This approach has an advantage. So actors fundamentally need to handle the fact that the message it is possible for the message to not be delivered instantly, for the message delivery to fail. So all actors written in Elfo already handle this case. This is like normal operation. The advantage of that is that you can introduce more cases where the message delivery fails. So usually software goes in the other direction, right? We want to reduce the number of failures, right? But we will take an innovative approach and we will make the number of failures higher by introducing some faulty medium like network. Sending and receiving messages is completely opaque to actors. They do not know how they are delivered, they do not know how they receive a message, they just know that they are somewhere there. So it is up to us to implement the connecting link between the two actors. This means that we can just put two actors on two different nodes. We can implement some kind of a network protocol between them, and for these actors it will seem same as if they were executing on the same node. Well, that's of course given the fact that your network protocol is not buggy. Of course, everything every sentence which starts with just is a lie, so there is actually a list of requirements we need to go through before this would actually work. First of all, we need to handle the message passing and routing. Once again, message passing is core to Elfo, so it needs to work reliably, and we need to support the routing logic between actors on different nodes. We also want the flow control, which is the alternative of the mechanism of limiting the actor mailbox size. We don't want the situation where an actor on one node sends a lot of messages, which the actor on the other node cannot handle. We want to somehow limit this stream of messages from the other node to avoid network congestion. We also want to, if possible, compress the messages, because it might be possible that the two actors are in completely different regions, and the network latency between them is really high. This means that we want to pack as much data as possible into the batch of bytes we send them. Finally, we want the system to be observable. If we are introducing more failures to the system, we want to be able to debug it. We want to have metrics, we want to have tracing, we want to provide all the tools for the developer to actually work and debug the system. At this point, you might ask, why not gRPC? gRPC implements a lot of things on this list. The main reason why my company at the time did not choose gRPC is these three. So first of all, we did not want to have any compatibility layer between Rust and gRPC. With gRPC, you define all the protocol in protobufs, and you generate the Rust code from these protobufs. So if you have some struct inside your application, it will need to be somehow converted into these protobufs to work, to be actually sent over the network. We also do not like the gRPC's type system, well, more like protobufs type system, which is not as expressive in Rust. Again, there is an extra friction in converting an enum or converting an enum from Rust into the gRPC, which we wanted to avoid. And finally, we believe that we will be able to provide a more efficient serialization than gRPC, more efficient in terms of the speed of compression and decompression. Protobuf is actually a very hungry protocol for CPU. It was developed under the assumptions that network is very expensive and the CPU is very cheap. Well, while that might be true for Google, that's not true for most of the companies. We decided that the best approach to represent the actors would be a network mesh. A network mesh is a simple thing where you have a cluster of nodes and each node is connected with all other nodes in the system. So here we have a cluster of just 3 nodes and each node is connected to all others. For this to work, we need two pieces. We need 2 pieces of logic. So first one is service discovery, and the second one is the actual connection between the nodes. Service discovery in Elfo right now is implemented in a very simple way. You just list all the nodes which are in your cluster, and the server will automatically try to connect to all of them. This list can be changed dynamically. For example, if you manage your configs using console or something like that, you can change the config on the fly, send an appropriate signal to Elfo, and it will try to connect to the new nodes you have added. Elfo supports not only TCP, but also UDS, which is faster protocol available when you're both of your services are on a single node, which is very convenient when your cluster is deployed in Kubernetes and you have two services which are physical on the same node but logically separate. To establish a connection between two nodes, we built two TCP sockets. I will call them TCP sockets for the ease of use, but bear in mind that it is completely possible to use UDS instead. So we established two connections. First one is control, and the second one is data. Control is mainly for the nodes to greet each other, to exchange what versions of the protocol they're using, what capabilities are there, can the node support, what kind of compression algorithms does the other node support, and which of the nodes will establish data connection. The data connection is actually like the meat of the topic. It's the connection we use to send all the messages and flow control data. So control is the low bandwidth with meta information, and the data is a connection which is very high bandwidth, which sends all the messages. In practice, however, we don't just keep one data connection per a pair of nodes. So you have one control connection between two nodes, but you have multiple data lanes associated with them. This is because each pair of actor groups, more like, have a separate data connection. This is again to avoid a very noisy actors from just congesting the data connection and to separate them not only logically but physically as well. So the data connection itself is a relatively simple thing. It has its wire format consists of two parts. First of all, we have a very simple format to encode message headers. These are things like what is the type of message? Is it a regular message? Is it a request? Is it a response? What is it? The length of a payload, the name of the message, and metadata like that. The actual message is encoded in message pack, which is not the most optimal format for this type of application because it is self-describing. So when you're looking at message pack, it's sort of like JSON. You have all the field names, and you can, without even having the description of your protocol, you can sort of devise you can parse parse the message from message pack. So we will talk about it later, how we can optimize it further. And finally, we do apply optional compression if it is enabled on data connection. Speaking about compression a little bit more, first of all, we did not use gzip. Gzip as a family of algorithms is older than me by 7 years. We really should stop using it as a default in the industry. There is almost always a better choice out there. And for us, this better choice was between LZ4 and ZSTD. For those who are not familiar, LZ4 provides a slightly worse compression rate than ZSTD, but at the same time, LZ4 is slightly faster at compressing and decompressing data. Since we are very latency sensitive, we decided to go with the LZ4, not ZSTD. So basically, a rule of thumb for us was that everything at rest is ZSTD, everything in flight is LZ4. The way the compression is implemented is that we buffer messages until some condition was met. If we just take a single message and we compress it with LZ4, we won't get much of a compression ratio. The algorithm needs more data to work efficiently. So we accumulate messages in the message batch for some time, then we compress the whole thing with LZ4 and send it as one big blob of data over the wire. The problem with this approach is that anytime you spend actually accumulating the messages in your message batch, is an added latency to these messages. So, for example, the message A was added the first here in the batch. Then when we have waited a little bit to add message B, message C, and maybe some more, we have improved the compression ratio, but all this time message A is waiting to be sent. So we have extended the latency of message A. We need to be really careful about that. LFO does some very basic heuristics based on the message size to decide whenever to send it or not. And in the future, we plan to implement more sophisticated algorithms to decide to balance the compression ratio and latency. Finally, let's get back to the problem of actors which can be overwhelmed. So here we have two nodes. And actor A on the first node is sending a lot of messages to actor B. Same as we had on a single node, if we just let this stand, the actor B will need to accumulate more and more messages. And this doesn't really make sense, because the processing power of actor B is for some reason much lower than the rate with which actor A actually sends the messages. So they will be piling up, accumulating, spending our memory, and most importantly, congesting our data connection, not allowing any other messages to come through. To fix that, we have taken an inspiration from the TCP, because we're basically implementing a network protocol on top of TCP, so might as well steal from the best. And we have implemented the flow control using windows. So a basic idea is that a window is number of messages an actor A can send without waiting for an acknowledgement from actor B. This means that, let's take a look at the example. If actor A sends 100 messages, and this means that the window of actor B is 0. It has spent all its budget for sending messages. After that, nothing happens. The actor A needs to wait until the actor B says that, hey, I have indeed processed all 100 messages that you sent before. Only then actor A can proceed, because otherwise, again, it will just send more and more data without actor B actually being able to process it. Once the actor B has sent an acknowledgement that, hey, yes, I indeed processed all the messages, the actor A can proceed with sending more, because their window has restored from 0 to 100. One of the things we do is that we monitor the speed with which the actor B is processing the messages. So if for some reason your system is overloaded and the processing power of actor B comes from 50 messages per second into 25 messages per second, this means that we need to update the window. We need to make sure that the actor A knows that, hey, the actor on the other side is really struggling. You need to send less of data, and we handle that by sending the appropriate window updates. Finally, this whole thing needs to be observable. Like we have introduced network into the play, which is famous to fail, and it's the truth of the reality we live in. Like we need to handle faulty network, and we need to be able to debug it. LFO tackles this problem from multiple perspectives. So first of all, LFO, even without having any network in play, provides you with so-called message dumps. Basically, you can flip a flag in a config, and the LFO will dump all the messages in the system, everything that has been sent, everything that has been received, everything will be in this log. There are two options. You can dump it in a file like I did, or you can dump it into some kind of an analytical database and run some interactive queries there. What this allows you to is to very quickly see how the system thinks. So when debugging the code, you already have access to your code, right? It's like in your editor, but you don't have the input data. And this message dump basically allows you to have this input data. You see exactly what is coming inside the actor, and from that, what kind of branches does it take, which really speeds up the debugging. LFO also has tracing. You might be familiar with tracing from OpenTelemetry. LFO understands tracing in a little bit different way. So trace ID is something that sticks to everything once you attach it. When you are handling an HTTP request, for example, you create a trace ID, and any events which you send from this actor while handling this request, you attach a trace ID to them. As soon as that happens, all the logs, all other messages which are generated by other actors while handling this message, all will have this attached trace ID with them. It means that you have a method to see everything which happens in your system which relates to a particular request or a particular operation. For example, your user might come to you and say that, hey, your server has returned HTTP 500 to me. Debug this error. If they provide a trace ID, you can go into the message dump, you can go into the logs and query by trace ID, and you will see all the messages which have been sent while handling this request. And of course, LFO provides a lot of metrics. For the single node use case, Elfo has already all the metrics you need to debug a local issue. This panel is only for one actor group, so you have the message rates, which are also splittable by the kind of message you are sending. You have the CPU usage, of course, you have the allocation rates, and much more. One of the most important metrics here is message waiting time. The system tracks how much time does the message spend in the actor's mailbox waiting to be handled. When you deploy Elfo with the use of the network feature, you get even more metrics which tell you about the volume of traffic between different groups, between different actor groups. It tells you how the flow control reacts to the system load. It tells you how much what are the window sizes of different actors, and again, much more. So you have a complete picture if there is an incident to debug and see what exactly went wrong. Finally, with some effort, you can build a picture of what a mesh looks like in your case. So you can derive from message dumps and from other metrics the structure of your cluster and see it in real time, seeing how many requests are being sent between different nodes. In this example, if you a bit zoom in, I'm not sure if it's visible on the back, but each edge on this mesh has the number of requests being sent. As an end result, we have an actor system which seamlessly mapped into the distributed network mesh. We have actors which have 0 to very little code changes now running on completely different nodes. None of this would be, of course, possible without the Rust ecosystem, because the main reason why this all works and why the developer experience is so good is because we have used the hell out of Rust macros, which are extremely expressive. We are privileged to have a native async support, which works really well. And of course, the Elfo is not Tokyo specific, like we want to support other runtimes as well. But Tokyo is what we have used in production, and we enjoy not thinking about async runtimes too much. What are the next steps for Elfo? So, as I said before, we can and will do a better serialization and gRPC. For that to work, we need to switch from message pack to some format which does not describe the schema, which is, well, that's not the correct way to say it, which is not self-describing. So again, message pack is self-describing because it has all the structure encoded, all the fields. You can deserialize it without having a schema. We don't really need that if both nodes speak the same protocol. Both nodes have the same definitions, have the same Rust struct definitions, so they already have what the data looks like. We can do this with using crates like postcard RS, which provide us exactly with that. They provide us with the non-self-describing format, which works really well if both ends of your connections know about the schema of your data. Expanding on the Kubernetes use case with the two services being physically on the same node, we want to support shared memory for communication as well. UDS is fine as all, but in our limited experiments, we were able to get a better throughput and latency from using the shared memory for communication instead of UDS. We want to be able, now that we're talking about the distributed system, we want to be able to think about parts of the system without specifying individual actors. So, for example, if you have a set of actors which handle what would be an appropriate example? If you have a set of networks which handle connections to database, for example, or connections to some external service, I do not want to select an individual actor in this group. I want to select the actor which has the best latency right now. So I basically want to be able to send a message and say that, hey, I want this message to be handled by an actor with tag ClickHouse, for example, and select the one which has the best latency right now, so that dynamically balances your system. If some parts of it are overloaded, you will just go to the ones which aren't. We want to provide more mechanisms on top of messages. So you already have seen requests. We also want to provide subscriptions. which are a bit tricky to implement in when your communication medium is faulty, but that's something we believe that this is a powerful pattern for developers to use. You can subscribe to updates from some actor or from a database or from something else and get all the updates in the form of messages, which is really useful. And finally, we want to support other runtimes. Again, we really enjoyed working with Tokyo, but we understand that this might not be the best solution for all. So we want to support other runtimes like Mini.io and stuff like that. Thank you very much.